In this worked example, we'll be looking at a beta plus decay. And the question reads, the decay of a nucleus argon 35 by beta plus emission is represented by this equation that you see here. It says a nucleus X and two particles beta plus and Y are produced by the decay. State the proton number and the nucleon number of nucleus X. A nucleus and two particles. Okay. So this beta plus particle has what charge? That's right, +1. Remember, if it's an electron, then it's -1. Like that kind of tells you right there. So this is the positron, right? Another name for this particle is the positron. So it has this +1 sort of number down here, but it itself is not a nucleon, right? So its nucleon number is 0, but its charge, okay, so think about it, its proton number is +1. So 1 plus something equals 18, right? We have to conserve nucleon numbers. And so the proton number is the one that goes down here, right? So it's like 1 plus 17, okay, so that's the proton number. 1 plus 17 would give us 18. So if there's no nucleons in this beta plus particle, all 35 nucleons must be preserved there. And so the nucleon number is 35. So what happened? The proton number went down, okay? It's like a proton became a neutron. And so the nucleon number doesn't change, because remember, this value on top is the number of both protons and neutrons. So this number decreases, but it's just that one of the positive charges, became a neutral charge. Okay, so the total number is still the same, it's just like we flipped the proton for a neutron. So the reaction that's sort of occurring here is that a proton became a neutron. And it emits, remember, a beta plus particle when it does that. That's this one. And then because, remember, this is a fancy antimatter particle, we just get the regular old electron neutrino. No bar on top for the antiparticle. And so you can kind of already anticipate what they're going to ask us here. This particle Y is what? It's this electron neutrino. So when they ask us about that, we already know, okay, it's the electron neutrino. Because we're calculating the nucleon number, like you say, well, is it fissioning? Like, remember, a big heavy atom like uranium or something is going to fission, not something like argon, okay? But argon can decay via this sort of, beta plus emission right here. So it emits a positron, a neutrino, and now it's no longer argon, it's fluorine. Okay, so like this X, if you look on the periodic table, what is something with 17 positive charges in the nucleus? Fluorine. The name of the particle represented by symbol Y, remember we said that that's a neutrino. Now it says, a hadron consists of 2 down quarks and 1 strange quark, determined in terms of the elementary charge E, the charge of this hadron. And that, by the sound of it, is your, yes, pop quiz. B up there. A hadron consists of 2 down quarks and 1 strange quark, determined in terms of the elementary charge E, the charge on this hadron. I'll give you 1.6 by 10 to the negative 19 seconds. Well, that's not fair. All right, so in your journal, you can put 310 pop quiz. This is question 7B. 7B. Does anybody need another minute or two? Or how about does anybody need -1 minute? Huh? -1 minute, anybody? Oh, that's a hint. All right, let's go -1 minutes. 3 minutes ago. Who's got the answer? Alyssa. -1 is it. So here's the way that I remembered it. And I don't know if I really like this mnemonic device, but if you think about, we had up, charm, and top. Okay, it's like up and top. Okay, that's all, like up, top, they kind of go together. But then you got down, well, it's like up, down, top, bottom, right? And then charm and strange. So these are the 6 flavors of quark. And remember, they all got anti-quarks, right? Like the anti-down, anti-up. So you got anti-protons. Just because the charge on this thing is -1 doesn't mean it's like an anti-proton, okay? Because an anti-proton would actually be, so if a proton is up, up, down, an anti-proton would be anti-up, anti-up, anti-down. That would give us an anti-proton. This is something that just happens to have a charge of -1 because the 2 down quarks each have a charge of -1/3. Remember, these are the guys with -1/3 from the notes yesterday. These are the guys with +2/3. So all of these are in the -1/3, right? Down and strange are all in the -1/3. So it's -1/3 plus -1/3 plus -1/3 is -3/3, which is -1. So -1 elementary charges. The same charge as an electron, except for an electron is an hadron, right? This is something that's made up of quarks, like one of those things. So this thing has like down, down strength. This doesn't really exist anywhere in nature besides in particle accelerators here on Earth, where we smash things together to try to mimic the energies very early on in the universe, which still can exist in the universe today in sort of rare places like cosmic rays that hit the Earth's upper atmosphere. Those energies are even higher than what we can achieve at the LHC, the Large Hadron Collider, right? That's sort of what we're colliding, protons and antiprotons. So here's the way to maybe remember it. It's like if up and top, they're positive, okay? And then you might think, well, what's a more positive trait? Charming or strangeness? And then that's where you can kind of say, well, I don't know, maybe there's something that's, I'd rather be charming than strange, so that's positive. If you like that, might be easy to remember. It's kind of like when we say, like, if you're learning the rules of multiplication, say negative times negative equals positive. And one of the ways this was taught to me was if a bad thing happens to a bad person, it's good. I'm like, well, is it really good though? Like, bad thing, even though they're a bad person, you don't want bad things to happen to them. But anyway, that's the way it was taught. Like, if a bad thing happens to a good person, it's bad. If a good thing happens to a good person, it's good, right? So multiply 2 positives, you get a positive. But if anyone is negative, it's negative. If a bad thing happens to a good person, or if a good thing happens to a bad person, it's bad. Right? But if a bad thing happens to a bad person, it's good. So multiplying 2 negatives is a positive. I don't know if I really agree with that. Just like I don't know if I really agree with, strange is negative, but the strange quark is negative, okay, and the charm quark is positive. So you need some way to sort of remember these charges associated with these quarks here to answer a question like this. All right, so in your journal, go ahead and list whether you earned 0 or 1 marks. If you got -1, you got the mark. If you weren't able to calculate this, 0 points, okay, on the top quiz. And I'll say that having a grade for the pop quiz is the assignment. So it's okay if you got a 0. Just give yourself feedback right now and go, oh, I didn't know what the charges were. I didn't look in my notes as to what they were. I don't have abstractions. Give yourself some feedback. And then when I go to grade journals, I'll look for just any grade. So the grade, whether it's a 0 or a 1, is worth 10 points, let's say. So it's 100 points a week for your journal. And when you go to submit your journal work, that's one of the things I'll look for. Did they do their pop quiz? And if I don't see evidence of that, then it's 10 points right off the top, right? You're down to a 90%. So just, it's okay to, to miss the mark on it, but give yourself feedback and learn and have a record of, the work that you're doing as usual. Any questions on that one? All right, so try your hand. At question number 40. All right, let's hear from an e-learning colleague. Have you found the correct answer to number 40? If so, unmute your mic and give us the letter of your selection, or type it in the chat. So this question emphasizes knowing not just the symbols, but what those symbols stand for, which is why I try to sort of write out underneath at least the core part of it, what they were. If you look at the other day where we just had sort of the beta plus and beta minus decay, we wrote out the words for that one too. So remember, what's another name for this beta plus particle? Positron, so that's what's being emitted. The positive charge is sort of being kicked out of the nucleus, and so the proton is becoming a neutron. So it's either C or D here, because you can see they all sort of have a proton becoming a neutron. But when that happens, it's like, well, where'd the positive charge go? Oh, it's in this positron. Okay. And so the correct answer here, check the chat. D. So if we get a positron, yes, we get a regular old neutrino. I always kind of remember it like that. Like only one fancy exotic antimatter particle. You get a positron, you don't get an antineutrino along with it. That's too much antimatter. You only get a regular old neutrino. Okay, so choice D is indeed correct. Well done. This has been another set of work example calculations and problems with Dr. Schleif. And we'll see you next time.